With all these work done, let's now look at a bigger example. It does not illustrate the scale challenge, which we'll come back very briefly in a moment, but it is slightly bigger than 4 nodes. Now we're talking about 8 nodes. Nodes 1, 2, 3, 4, 5, 6, 7, representing 8 web pages interconnected by directional links, these hyperlinks. If we just stare at this graph and say, which node is most important? Well, we may say by degree, in degree count, node 4 is the most important. Right? Because it's got 4, it's bigger than any of the other nodes in degrees. But if you think along the line of Google PageRank, which implicitly assumes certain navigation behavior, you see that 4 basically gives away all this importance score to a single node downstream 3. And 3 does not give it back to 4. Okay, it spreads it further to 2 and 8. So this gives you a hesitation that maybe node 3 by PageRank calculation of importance score will be higher than 4. And indeed, we see that's the case. Intuitively, 2, 3, 4 should be highly ranked, and that is what we will see. And which nodes will have the least importance score? Well, those nodes that are not pointed by many other important nodes who concentrate on them. And we can see probably node 7 and node 6 will have low importance scores. And indeed, that's the intuition will confirm in a short while. These will be lowly ranked, will be highly ranked. So to make this a little more efficient, I've written out the H matrix already, okay, just based on the topology of this given graph here. Now we can then construct H hat, but H hat is the same as H because there's no dangling nodes. And then we can construct matrix G with randomization parameter, or anti-randomization parameter being 85%. And then 15% of the time we'll be doing random hopping among the pages. Then you can write down that G matrix, and then you can start doing the iteration pi equals pi transpose equals pi transpose G from one iteration to the next. And this shows the first initialization. All the nodes have 1/8 exactly evenly distributed. It doesn't matter what initialization you use, actually. It will change the convergence speed a little, but not the end result. The first iteration is shown here. It's this vector, okay, and I'm skipping the other steps. You can see that in the textbook. Eventually, it converges to this, or something like this. Actually, this is only the 6th iteration, but it's getting quite close to the final answer. The final answer is shown here. This is the equilibrium pi vector for the 8 nodes. I have already ordered them, and I have already normalized them. So what you see here is the normalized and ordered by the importance scores in descending order. So node 3 has the highest importance score and therefore ranked number 1, followed by node 2, followed by node 4. You can see node 3 actually is by far the most important. 0.2 sounds like a small number, but remember the pi is now normalized, so it all add up to 1. So 0.2 out of 8 nodes is actually quite impressive. 2 and 4 are about the same, and nodes 6 and 7 are by far the smallest. Okay, that's 0.06, 0.04. But then again, Google PageRank returns the ranking. It does not show you the actual scaling. So the scaling is only intermediate step. And this confirms our intuition, what we just said before, that node 3 perhaps is the most important, even though node 4 has a higher in degree. That's because PageRank calculation models the navigation behavior, saying that if a lot of people come to this web page, but then they all have to go out to this page, then this page actually shares 100% of the importance score spreading from node 4.